Let me just briefly recap what we did last time. So last time we looked at first order algorithms. By first order we mean gradient based. And we saw that for different classes of functions, we had different convergence rates for gradient descent, and then for the class of smooth functions, we had Nesterow's accelerated gradient descent, which achieves a faster convergence rate than gradient descent, right? So we had gradient descent. And the classes of functions that we looked at were, one was Lipschitz, and the second one was smooth functions. Smooth meaning that gradients are Lipschitz. Okay, so this is basically what we covered in the last lecture. So today this is what I want to do. So first I want to talk about another class of functions which are smooth and strongly convex functions. So these are all convex, right? Smooth and strongly convex functions. I'll define what strong convexity means and what is the convergence rate that gradient descent can get for these class of functions. Okay, and so far all of these assume that we have access to an exact gradient. So we query the gradient at a point and we get the exact value of the gradient at that point, right? In the after this, in the next part, we will talk about stochastic algorithms, where we will not compute gradients exactly, or we may not have access to gradients exactly, or we may not want to compute the gradients exactly because it's way too expensive. So you'll only have a random vector, which in expectation will be the gradient, but it will have some amount of randomness. And we will see what are the algorithms that can help us deal with this kind of scenarios where the gradients are not really available exactly, or computing the exact gradient takes a long time. Okay. So within this, I'll first talk about stochastic gradient descent. And for what are known as finite sum problems, I'll again explain all of this, and I just want to give you an overview of like what I'm going to be talking about. So for problems which are known as finite sum problems, we will discuss a recent algorithm, recent being like 6 years old, stochastic variance reduced gradient. Also called SVRG. Okay, and finally, if we have time, I'll briefly talk about non-convex optimization. Okay, so this will be the outline of what we'll be covering today. Okay, so we know what smoothness is. So smoothness, let's recall smoothness from the previous lecture. Smoothness basically says that the gradients are Lipschitz. Okay, and an important implication of this was that for any 2 points x and y, the function f satisfies this property. Okay. Okay, so let me now define strong convexity. So, okay, so just convexity is this. Okay. So this is just convexity. This is just the definition of convexity. Strong convexity just says that we have a bound on the difference between these two things. And mu is the parameter of strong convexity. Okay, this is equivalent to saying, okay, so if the function is twice differentiable, then convexity is equivalent to the Hessian being positive semi-definite, and strong convexity is equivalent to the gradient, the Hessian being greater than or equal to mu times identity. Okay. So a simple example would be if you take a quadratic function. So let's say I want to do min over x. Right, strong convexity is equivalent to okay. So for linear regression problems, for example, where we are looking at a quadratic function, strong convexity is equivalent to requiring that the covariance matrix of the data points that we have is greater than or equal to some constant mu times identity. Okay. So we would like to see what gradient descent, what is the rate that gradient descent can achieve on functions which satisfy both these properties. So in the last lecture, we have not really looked at this property. We just assumed convexity with mu is equal to 0. And if there is a parameter, if the function satisfies this inequality with mu which is strictly greater than 0, then we will see if we can do something better than whatever we could do the last time. Okay. So gradient descent again is this. So the theorem is as follows. So sorry, this is matrix PSD ordering, positive semi-definite ordering. Yeah. Okay. So what this says is if the function, in addition to being L smooth, is also mu strongly convex, then gradient descent achieves, after t iterations, achieves a suboptimality of at most some constant which is strictly less than 1 to the t. So this goes down geometry like exponentially fast in terms of t times the initial suboptimality. Okay, and the proof is actually fairly simple. So we again look at xt plus 1 minus x star. So we'll just use this update. Okay, so by smoothness, we had that so this follows from the last lecture. We did this in the last lecture, and by strong convexity, okay. So this term we upper bounded by the smoothness parameter times the suboptimality from the last lecture, and if we apply the definition of strong convexity between xt and x star, we know that f of x star is greater than or equal to f of xt plus this term plus that term. So just interchanging terms, we see that this gradient and inner product term is greater than not just the function suboptimality but also this additional term, right? So just plugging these two things in, we see that okay. So just plugging these two equations in this. So this mu over 2 basically comes in here and we get a geometric decrease here, and as long as we ensure that this term is negative, we have a geometric decay in terms of xt converging towards x star, right? So let's see it. So unrolling this gives us and this can also be converted into function values because f of xt minus f of x star is less than or equal to So this guarantee can then be converted just into in terms of function values. So what we see is that once we have strong convexity, which is defined here, we see that the convergence rate is actually geometric. So in particular, so just for comparison, so for Lipschitz, the error was of order O of 1 over square root t. Sorry? We did this in the last lecture by using smoothness, yeah. So just comparing the results from last lecture. So for Lipschitz functions, we saw that gradient descent achieves a rate of 1 over square root t. For smooth functions, gradient descent gets a rate of 1 over t. Again for smooth functions, Nestrov's accelerated gradient gets a rate of 1 over t square. For smooth and strongly convex, gradient descent gets its geometric rate, which depends on what is known as condition number of the problem. So the condition number is defined as the smoothness over the strong convexity parameter. So this is basically 1 minus 1 over condition number to the t. And it turns out that we can again do the Nestrov acceleration idea that we did for smooth functions. And this again improves this rate. So if we use that, we get something like of 1 minus square root of mu over L to the t with AGT. Yeah, maybe there is a 2. Sorry? Yeah, there is a constant factor here. Yeah. Okay. Okay, so we see that as the functions have nicer and nicer structure, so from here to here, we saw that like having smoothness in higher order derivatives gives us an improved rate, and from here to here, we saw that having more curvature also gives us a significant improvement. So in general, in optimization theory, these are broadly like the 4 most widely studied classes of black box optimization problems. Okay, so let's come to stochastic setting. And in particular, let's look at what's called stochastic gradient descent. Okay. So the setting where people initially, okay, so this algorithm itself and the setting itself was originally considered by Robbins and Monroe back in the 1950s. So they were looking at a problem of this sort where the function f is actually given as an expectation. where this zeta is a random variable, and in general the gradient of f actually is equal to an expectation over the gradients of g, where you again have to take the expectation over these random variables. And in practice, we never can compute expectations exactly, right? So we can only sample some number of samples from this distribution, let's say, and then we'll be able to compute, say, an approximate expectation, but we will never be able to compute exact expectations. So Robinson and Monroe were trying to design algorithms which can actually do optimization in this kind of setting, where the gradient is never given to us exactly. We have to sample, and any number of samples will still result in some amount of error. And you would like to understand what is the optimality that you can get to with a given number of samples. Okay, and the algorithm that they proposed is actually a very natural extension of gradient descent. So what they did is something like this. Where are all independently drawn from the same distribution. Okay. So a more general way of writing this is just that at every instant we have access to a stochastic gradient and what we mean by stochastic gradient is the following, that stochastic gradient grad hat f such that and furthermore we'll assume that this has bounded variance. Okay. So at every time instant we have access to a stochastic gradient, and the stochastic gradient satisfies two properties. The first one is that its expectation is exactly equal to the true gradient of the function, and the second one is that its variance is bounded by some quantity sigma square. And we would like to understand convergence rate of stochastic gradient descent with respect to the parameter sigma square and other parameters of the function. Okay. So this is what we can say about stochastic gradient descent. If f is G Lipschitz, and we have access to stochastic gradient oracle, with variance sigma squared, then stochastic gradient oracle. So these are so stochastic gradient oracle give me a grad hat f which satisfies these two properties. So grad hat f is a okay. So I give it an x, and it gives me a random vector grad hat f, and the grad hat f satisfies these two properties. So grad hat f of x, its expectation.
So in the structure you have over there, you would be having access to a sample of the sub.
Yeah, exactly. Yeah. So okay, so if you run stochastic gradient descent with a step size of eta, then what this theorem says is that the expected suboptimality of the average iterate, so xt are the iterates that we have, right? We take an average of all the iterates that we have seen so far after t steps, then the expected suboptimality of this average iterate is at most x0 minus x star square, so this is the initial distance divided by eta t, and then we have g is the Lipschitz constant and sigma is the variance of the stochastic gradient oracle. Okay. So we can, so again we can set eta to be norm x0 minus x star divided by square root of g square plus sigma square times square root t, and then we will get the RHS right hand side here is less than or equal to, rather it's equal to So any questions on the setting or the result before we go on to prove? Okay. So just to recap, so we are looking at the stochastic setting where we don't have access to exact gradients. I mean, either the function is actually explicitly written as an expectation and we cannot really compute the exact gradient, or computing an exact gradient is way too slow because maybe the expectation is maybe over a discrete set, but a discrete, like very large discrete set, we cannot really afford to compute the entire expectation. So in this case, you would maybe sample say one particular value of zeta and then compute the grad with respect to x of g of xt zeta t. This in expectation will indeed be the true gradient of the function. And the other thing we are assuming about this stochastic thing is that it has variance bounded by sigma square. Okay, and under this condition, whenever we have access to these grad hat f of x, the algorithm we will be using is the stochastic gradient descent algorithm, where this will in general be grad hat f of x t. Okay. Okay. And once we have this, the result says that the expected function value suboptimality after t iterations goes down as 1 over square root t. I mean, yeah, you can get high probability bounds, but that requires, so here we are only assuming that the random variable has bounded variance, right? When you have these things to have like tails, then you can use that to get high probability bounds on this one. Yeah, yeah.
So the bounds on the f of the expectation, and stronger thing about, so the previous thing was slightly stronger because about expectation of the f, like time.
Yeah, so actually that's basically what you get. So there are two things you could do from that point. You could either pick, so in the previous thing, for example, you could keep track of the minimum, because you were indeed able to evaluate the function exactly. Here you may not be evaluate the function exactly because the function itself is an expectation. So either you can pick one of the iterates at random, or you can just output an average of all the things, and this is also fine due to convexity. So I'm saying the bound indeed will be that 1 over t. Yeah. This is basically the bound we'll get, and then this is a weaker version. Yeah. 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 I'm assuming f is convex. Yeah. G could be anything. F is convex. Yeah. 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 So yeah. So this was basically what I was. Yeah. Even here, I'm assuming that they're all independent. Yeah. Yeah. So the stochastic gradient at each iteration that I'm getting are basically independent of all the other stochastic gradients that I'm going to get. So each of them is independent. So the proof is actually not too different from what we did yesterday. So we'll look at xt plus 1 minus x star square in expectation. So this is just expanding the square. So because grad hat f of xt is basically independent of xt, so I can take an expectation only over the randomness in grad hat f, conditioning on xt. This will be grad f of xt. And the variance, so this term can be bounded as the norm square of the expectation, sorry, yeah, plus the variance. Right? I'm just saying that the second moment is the sum of the mean square plus the variance. And by assumption, so we see that so this is by convexity. Okay. So all that remains is to telescope and average. Okay, so this will basically give you this result. Is the argument clear? So the proof is essentially like almost exactly the same as what we did yesterday, except for we were working in expectations, and maybe the only two differences are that we know that the grad hat f is independent of the randomness in grad hat f is independent of xt. So we take the expectation with respect to that randomness first. So we'll get just grad f of xt, and this by convexity can be bounded by f of xt minus f of x star. And the second thing is we have this second moment of the gradient, stochastic gradient, that can be written as the sum of the mean square plus the variance, and both of them are bounded by g and sigma respectively, right? Okay, so this is when we have the function to be g Lipschitz. So we are always assuming that the function is convex. Okay, okay. So if we actually assume that if the function is not just Lipschitz but also has higher order smoothness derivatives, then we can separate the dependence on the noise and then the function dependent parameters. In particular, if f is L smooth, then if you use gradient descent appropriately, what you get is the expected suboptimality. So let me be somewhat vague here. Is less than or equal to L times norm of x0 minus x star square divided by t plus sigma norm x0 minus x star divided by square root t. So we can actually, okay, so once we have any amount of noise, it turns out that the 1 over square root t rate is the best we can do in the worst case sense. So yesterday I mentioned about black box lower bounds for any gradient based algorithm which can only query gradients, right? So for the Lipschitz setting, we saw that the 1 over square root t convergence rate we got was tight, and I also mentioned that for smooth functions, the 1 over t square rate that accelerated gradient descent gets, that's also tight. Similarly, we can show that whenever there is some amount of noise, asymptotically, you cannot really do better than this 1 over square root t. Okay, but so the bound that we got here, however, had a, here has a g also on the top, right? But if the function is actually well behaved than just having bounded gradients, you can actually separate out the dependence into a 1 over t dependence for gradient descent, and you can also fuse. You can also construct a stochastic version of Nesterov's accelerated gradient that will actually get a 1 over t square here, and then still have a 1 over square root t here. So it's optimal both on the function parameters and on the noise parameter. Okay, so this part is clear. Yeah, so if you have strong convexity, actually it turns out that you can get a 1 over t rate. You'll not have, yeah, with exponential decay on this part, but and a 1 over t instead of 1 over square root t here. Okay, so let me now talk about stochastic variance reduced gradient. Okay, so the motivation for considering this algorithm comes from what is known as the finite sum setting. So where my function is given by the sum of or the average of n different functions. So as an example, for let's say we are doing linear regression. Where we have say n data points, and then the function that we wish to minimize is the following. Right? Okay, so let's say we want to apply gradient descent to solve this problem, right? Okay, so first let's say the function is actually, okay, each of these is smooth and strongly convex. So let's say okay, so L is basically the norm of 1 over n and mu is the minimum singular value. Right? If we apply gradient descent for smooth and strongly convex functions, we know that the number of iterations it takes is equal to, I'll write it in a different way, L over mu log 1 over epsilon, where epsilon is the desired accuracy, right? So what we saw was error is less than or equal to say 1 minus mu over 2L to the t. So if I want an error of epsilon, then this implies t has to be of the order of L over mu log 1 over epsilon. Right? So this was the first convergence rate we got for smooth and strongly convex functions today. So I'm just writing so that was basically the error as a function of the number of iterations. I'm just reversing it to say if I want like epsilon suboptimality, what is the number of iterations I need to compute. And the number of iterations for gradient descent is L over mu log 1 over epsilon, right? And the amount of time taken to compute a single gradient, single step is, let's say each of these AI is in RD. It's n times d. Is this clear? So the number of iterations which we got from the convergence rate of gradient descent is L over mu log 1 over epsilon. And what does each iteration involve? We need to compute the gradient. What is the gradient? We first need to compute, okay. So the gradient is 1 over n summation I equal to 1 to n AI transpose X minus BI times AI. So we basically have to look at all the AIs, right? And each AI is a d-dimensional vector and there are n of them. So the total amount of time we need to take a look at all of them is nd. So each iteration costs us nd amount of time and the number of iterations is L over mu times log 1 over epsilon. Okay. Now let's see what SGD can do. Here the number of iterations is sigma square so for SGD what did we get? So error was less than or equal to sigma x0 minus x star divided by square root t, right? So if error was epsilon, then t would be sigma square norm x0 minus x star square divided by epsilon square, right? This will be the number of iterations required for stochastic gradient descent to reach an accuracy of epsilon. And a simple computation here shows that sigma is basically of the order of max over I norm I square, because you can just compute the stochastic gradient at x equal to x star, right? There the gradient is equal to 0, and if you compute the stochastic gradient there, then the variance is of the, or rather expected value of right. So we were looking at the gradient being bounded, so it's basically so the number of iterations of stochastic gradient descent depended on the variance in the stochastic gradients, and that is captured by expected value of norm ai square, right? And epsilon is the desired accuracy, and the convergence rate was 1 over square root t, so the convergence rate is more like 1 over epsilon square. Number of iterations required is 1 over epsilon square. And in order to, so the number of single iteration cost here is that we'll sample a random AI and then we'll just compute AI transpose X minus BI times AI, right? We'll just pick a single vector and then compute gradient with respect to that particular vector. So the single iteration cost is only D. So the total amount of cost to achieve epsilon accuracy for stochastic gradient descent is D times this number over epsilon square, right? Whereas if we were to implement a full gradient descent, then the cost was ND times the condition number times log 1 over epsilon. Okay. So these are the two different algorithms that we saw, and the important thing to note here is that this one has a very fast convergence because it's only depending logarithmically on the desired accuracy epsilon, right? However, it does depend on linearly on the number of data points n, and it in fact multiplies this n with this condition number, which could in general be pretty large. Okay. On the other hand, what stochastic gradient descent can do is it almost does not even depend on this factor n. However, in order to get very high accuracy, you really need a large number of iterations because the error goes down only as 1 over square root t. So the main idea of stochastic variance reduced gradient is whether we can get the best of both of these into a single algorithm, so that the dependence on n is not really multiplied by a condition number, which is a huge factor, and at the same time we retain the geometric convergence rate that gradient descent has. So stochastic gradient descent, as you go closer and closer to the optimum, is not good. So you would want to do something gradient descent like when you are closer to the optimum. so that you still retain this fast convergence rate while not paying a multiplicative factor in terms of this condition number on top of this sample size. Okay. Yeah. So this itself, if you don't care about the making epsilon to be super small, there is no dependence on n. Yeah. But once you want some kind of geometric convergence rate, there will be a dependence on n. But as long as epsilon is something which is independent of n.
There is a dependence on that. Because the constant you have here is not correct. You have the maximum of the expectation of the AI squared.
So for each I, this AI is fixed, right?
Yeah, but you can tell us how the AI are choosing.
Yeah, so the norm of AI itself could have some dependence on n. Yeah.
Maximum of n terms. You didn't write it, but it should be the maximum.
Oh, by the way, I just meant the I is chosen uniformly at random from all the from 1 to n, and then this is just the expected value of the norm square. So for each I, the norm of AI is fixed, right?
Yeah, then this thing depends on n too.
Yeah, this could depend on n. Yeah, there. Norm square need not depend on n. The norm square need not depend on n. I mean, AI could all be just unit vectors. AI are fixed, they could even be unit vectors. So, I mean, in that case, there may be something which comes in the condition number and so on, but a priori, this need not depend on n unless epsilon, the desired accuracy that you are requiring is something which is of the order of n or something polynomial in n. Yeah, actually, there is some connection between like the smoothness here and norms of AI square here, because the L is the operator norm of this matrix, which is the average of all of these, right? So there is a connection between L and norm of AI, but for now, I think it suffices to generally think that if you take the product here, n times L over mu is much larger compared to AI is a data point. So AI, BI are the data points, and then X is my parameter vector. Okay, so let me describe the main idea behind stochastic variance reduced gradient. The main intuition is that the number of iterations depends basically on the variance of the stochastic gradients, and as I move closer and closer to the optimum, if I can keep reducing the variance in the gradient, then I can get faster convergence rate. Okay, so the basic update of SVRG is the following. So you fix an x0 and compute the gradient at this point, the exact gradient. Okay. So the iteration is the following. So if I had just used this is just stochastic gradient descent, right? Xt minus grad fit. So it is chosen again uniformly at random from 1 to n. Okay. So because it is chosen uniformly at random from 1 to n, this is indeed a stochastic gradient whose expectation is equal to the gradient, but I am adding some other term which is mean 0, because if I take expectation over of these two terms, this one is fixed, and if I take an expectation of this again with respect to it, this is again the gradient f of x0, so both of these cancel, right? I am adding a mean 0 term to the stochastic gradient. But what I'm hoping, the reason I'm doing this is that it will indeed, I hope that this will reduce the variance of this whole estimate, so that when I'm closer to the optimum, I will converge much faster. And as a simple example, suppose if you actually start at x0 equal to x star, right? If you start at the optimum, then you actually don't move. Whereas stochastic gradient descent, even if you are indeed at the optimum where gradient, the full gradient is equal to 0, stochastic gradients will always be non-zero, right? So you'll end up moving whenever you make a stochastic gradient step, whereas if you do this step, you will never end up moving. Okay. So we'll see what's the convergence rate of this algorithm. So this is the theorem. If each fi is convex and L smooth, f is mu strongly convex, then so after t iterations, so what this says is I start at some x0 and then I compute the exact gradient at x0 and then I do these iterations for say t number of iterations. Then this is saying that the average suboptimality after t iterations is at most some constant which depends on the step size, number of iterations, the smoothness and strong convexity parameters times the initial suboptimality. Okay. So if I can make sure, so there are two things under my control, one is the step size and the other one is number of iterations I ran for. If I can choose both of them so that this is a constant which is strictly less than 1, say half, then this basically says that after t iterations I have a geometric decrease, I have a constant factor decrease in terms of the function value. So I will then be able to use this to get a geometric convergence rate. Okay. So if I choose eta equal to say 1 over 4L and t equal to 16 L over mu, then this will be less than or equal to So if I choose a step size which is like 1 over 4L and number of iterations T which is 16 times the condition number, then the average suboptimality of these many iterates is at most say half. So this will be half times the initial suboptimality, right? And then I can again repeat this procedure by setting by choosing the average point here and choosing it to be x0. I'll again compute the full gradient and again I'll go through the same process. There are other algorithms, but I think all of them essentially have like similar ideas. There is no other mechanism that can give you something like this. There are definitely other algorithms. There's a dual coordinate ascent and so on, but all of them have this kind of mechanism to actually make it work. Yeah. Okay, so let's try to just prove this result. So we'll again look at expected value of norm xt plus 1 minus x star square, and this is equal to expected value of okay. So I'm just substituting the update for xt plus 1 that we had. So the first term is again the norm squared. The second term will be the cross term. Okay. So in this term, because IT is chosen independently uniformly and the expectation of this is the same as this term just cancels. And by convexity, we can again see that this is less than or equal to the function values of optimality. Plus eta square, the variance term. Okay. So all we need to do is compute the squared, norm squared of this quantity. so this is less than or equal to 2 times expected value of the square plus the expected value of x0 square, right? A plus b whole square is less than 2a square plus 2b square, and this one again we can, so ignoring constant factors up to one more factor of 2, so we see that this is less than or equal to 4 times. So we will add and subtract grad fit of x star. So okay, so this term remains the same, and for this term we are just adding and subtracting grad fit of x star, and then using yeah. Where we begin meaning x0. That's true because the variance bound that we will get will depend on how far x0 is from x star. So as you get closer and closer, the variance will depend on something like the function value difference between x0 and x star. So actually this term using smoothness is again kind of easy to bound. So this is just less than or equal to 4L f of x0 minus f of x star by smoothness. We have already used, we have already showed this bound in both the previous lecture, and both of these two terms have a similar form. We have a point x, and then we are looking at the norm square difference between grad fit of x minus grad fit of x star, right? Here it's xt and here it's x0, but both of them have the same form. So we will just try to bound the norm square of this thing. Yeah.
After every t steps, we will have to compute the full gradient.
Yeah, yeah.
So it will still depend on n.
It will still depend on n, but I'll tell you what the final bound will be and how it compares with gradient descent and S2. Yeah. Okay. Okay, so in order to do this, let's consider this. So gi, so let's define gi of x to be fi of x minus grad fi of x star comma x. Okay, so fi's are the functions that were given to us, right? And we are defining a new function gi of x to be fi of x minus a linear term. The reason we are subtracting this linear term is because grad gi of x star is equal to 0. And we also assume that each of the functions fi is convex, and convex minus a linear term is still a convex function, right? So since the gradient of this convex function at x star is equal to 0, x star is indeed the optimum of this function. So what we know is that gi of x star is less than or equal to gi of x minus let's say 1 over L right. So x star is the optimum, so gi of x star is less than or equal to gi at any other point. And because we also assume that fi is smooth and this one is only a linear term, so gi is also smooth. So this means that this is less than or equal to gi of x minus 1 over L grad gi of x with grad gi of x plus L over 2 times 1 over L square norm grad gi of x square. Okay, so this is clear. So the reason we are looking at something like this is because this grad gi of x is exactly equal to grad fi of x minus grad fi of x star, which is basically what we have here, right? So when we sum over all of these, we will be able to get this expectation. So the expectation there so which is the same as 1 over n right. This is by definition of gi because gradient here is gradient fi of x minus gradient fi of x star. And now we can use this. So this quantity is less than or equal to 2L times gi of x minus gi of x star. So let's now plug in the values of gi of gi. So we just plugged in the values of gi. So gi has two components. One is the function itself, and then there is a linear term. And when I take the sum of the gradient from I equal to 1 to n of grad f of I, actually end up getting so there is 2l over n times, sorry. So when I take the average 1 over n, I will get 2l times f of x minus f of x star and plus grad f of x star times x star minus x. Because x star is the optimum of f, this is equal to 0, right? So this is equal to 0. So what we have seen is that this variance is less than or equal to 2l times f of x minus f of x star. Okay, so now we should go back and plug this in this expression. So expected value of is less than or equal to xt minus x star square minus 2 eta plus eta square times this variance term. From this we get to here. So we have so there is a 4 here and there is a 12 there. So overall you will have 8l expected value of f of xt minus f of x star plus 8l f of x0 minus f of x star, and we have one more 4l here. Okay, so this term can be absorbed into this. So we have a negative eta and then positive eta square. So at least this term can be absorbed in here. Okay. So what we have seen is that the potential at so the distance to optimality of xt plus 1 is at most xt minus x star square minus a term which depends on the function values of optimality at t plus something. This is the variance, I mean this is the real variance term which depends on the difference between the function values of optimality at x0 compared to x star, which is the point where we compute the full gradient at. So this is basically the amount of variance reduction that we are getting. Earlier if we did not do this variance reduction, we would have gotten a constant term here, whereas because we are computing a full gradient at x0 and then adding a term, mean zero term to decrease the variance, the reduced variance is actually this. And once we do a telescope of this and use the strong convexity parameter. So far we have not used strong convexity. So once we do a telescope and telescope and use strong convexity. To prove the statement of the theorem. Okay. So okay, so let's now maybe in the last 5 minutes, let's try to compare the rates of gradient descent, stochastic gradient descent and the SVRG because you are not.
Introduce this last thing.
Sorry?
Who introduced this last thing, this reduced variance?
I mean this, sorry, what name?
What name, who did it?
Johnson and Zhang, Rai Johnson and Tong Zhang. I can send you a link to the paper, yeah. It's from 2013.
2013.
13, yeah. Johnson and Zhang. Okay, so let's just again okay, so F is 1 over n summation Fi, right? So let's say Lf is smoothness of F. Mu is strong convexity of F. And let's say L is smoothness of each Fi. Okay. So gradient descent requires n times d. This is the amount of time taken for each gradient computation times condition number, which is Lf over mu, and then log 1 over epsilon. This is the number of iterations required for gradient descent. For stochastic gradient descent, each iteration takes only, also you need, I guess, max norm of the gradient. So this requires d is the amount computation, and then it will be g square SVRG. What SVRG takes is, whenever we compute the full gradient, it will take nd, and the number of iterations we need to run turns out to be about a condition number. So that's the condition number here is actually L over mu times d log 1 over epsilon. So in order to compute one full gradient, we require nd time, and once we compute one full gradient, the number of iterations that we run is L over mu, right? and for running each iteration we require a stochastic gradient computation which takes about d time, right? So this is the time. So if we try to instantiate in the context of linear regression, so fi of x is equal to aix minus bi whole square. Okay. So LF is 1 over n summation over I. Yeah, yeah. Then this factor is pretty large, and whereas here that factor does not even multiply n. Yeah. Right. So I guess the only thing we need to be clear about is we have a different L here, and we have an LF here, right? So can L be of the same order as LF times n? In which case this will not be useful, right? So the only question we need to ask is L like significantly smaller than LF times n. So only if this is the case that we get an improved convergence rate compared to this, right? Because L and LF are actually different. And so in order to compare that, so LF is just the maximum singular value here, and L is the max over I norm of AI square. Right? So for example, all vectors can be unit norm, in which case, okay. So I'll give you a simple situation in which this is definitely true, and that will give you at least one example of in what kind of situations will SVRG be actually much faster than gradient descent, right? So consider the situation where each vector is unit norm, okay, but somehow the vectors actually have a much the covariance matrix is actually very concentrated uh, on the top direction, right? So and right. So maybe let me write it here. So this is basically if you sample AIs from a Gaussian distribution where the covariance matrix looks something like this, right? Each vector will basically be of the same norm, right? So each vector will be of norm about 1. On the other hand, if you look at the operator norm, it's again still a constant, which is only a constant factor away from the norm of the vector, right? So in this case, L is basically of the same order as LF, right? Here we suffer an extra factor of n multiplying it, whereas here we are able to separate them into two additive terms. So this can be much faster than this one, and in situations where the largest eigenvector can be significantly large and the matrix can be quite imbalanced. Those are the settings where SVRG can actually help improve the convergence rate both compared to gradient descent and compared to stochastic gradient descent. Okay, so I think I'll stop here.